Good morning, everyone. I would like to begin by thanking the organizers of this meeting for inviting me. It's an honor and a delight to see many familiar faces I haven't seen in a long time. Today, I'm going to talk about the consequences that macular degeneration has for the control of eye movements. In particular, the problems scientists face when they are trying to measure the eye movements of people with central vision loss. The symptoms of macular degeneration are well known. They include low acuity and contrasensitivity, poor color vision, metamorphopsia in some cases, and all of this leads to difficulties recognizing faces, reading, and in general, performing any task that requires the ability to see fine detail. However, and more importantly, macular degeneration affects the controls of the movements of the eyes. I'm going to illustrate this with two slides. The first one shows how visual acuity decreases with the distance from the fovea. At only 5 degrees eccentricity, we have only 40% of the acuity we would have at the fovea. On the other hand, the brain has the task of controlling 6 pairs of extraocular muscles in order to rotate the eyes so that the image of the object of interest falls within a very tiny area, which is about 1.5 millimeters, depending on how you measure and what you measure, but it's a very small area. Eye movements are usually classified into 2 systems. You have the new systems, which evolved with the fovea and are most affected by the loss of the oculomotor reference, and the old systems. The new systems include saccades, vergence, fixation, stability, and pursuit, although pursuit is not necessarily foveal. And then you have the old systems, vestibular ocular reflex and optokinetic nystagmus. I'm going to show you a demonstration, a simulation of someone who is trying to read Moby Dick, but is unaware of the scotoma and or the effects of the movements of the eyes. The standard complaint is that things just appear and disappear. These people can be helped. There is a common adaptation to the loss of central vision loss, which is the development of the PRL, or preferred retinal locus. It involves moving the eyes so that the image of the object of interest lands in a relatively healthy part of the retina. In this particular image given to me by August Collenbrander, this gentleman was asked to look straight into the camera. And what he does is look up, use his lower visual field, that is the upper part of his retina, in what is now the new straight ahead for him. Now, the location of the PRL affects reading performance. One obvious reason is the fact that both the physiological and the pathological blind spots simply make part of the text unreadable. PRLs above and below the scotoma on the retina are best because there is more real estate for reading. Perhaps the upper retina, which involves the lower visual field, is better because of its relation to locomotion. However, the problems with reading are not only the fact that the text is partially or completely made invisible by the scotoma, it's also the fact that saccades, both forward and regressive saccades, are damaged or made very difficult by the presence of the scotoma. Okay, so in general, we have up until now measured eye movements in people with macular degeneration two ways. Either we have used scanning laser ophthalmoscopes or microperimeters, which are the gold standards for measuring PRL location relative to anatomical landmarks. The problem with these systems is that they have low sampling rates, although that can be made a bit better with the software. They have simple graphics, but the real problem is that they are monocular systems. On the other hand, we have video-based eye trackers. What a video-based eye tracker is, it analyzes the features of the eye from a video image. The software determines the centroid of the pupil or the center of the pupil, centroid of the pupil, plus one or more first Purkinje images, usually produced by infrared beams. They have high sampling rates, they're easy to use. They are for monocular or binocular viewing. The head can be monitored, the hand can be monitored, the whole body can be monitored. They have sophisticated graphics. The problem is the gaze is assumed to be foveal, so the PRL location has to be inferred. So how do we infer the location of the PRL? Well, we can measure the monocular PRLs using a scanning laser ophthalmoscope or a microperimeter, and then just simply adjust the calibrated eye positions yielded by the eye tracker. On the other hand, we can use angle kappa and compare the angle kappas of people with normal fovea and the angles kappa of patients with macular degeneration. And then we transform all of that into world coordinates using relatively simple geometry. We did this in 2015. And I'll tell you how, but first I'm going to define angle kappa. This is angle kappa, just the horizontal component of angle kappa. And it is the angle subtended by the visual axis, which connects the fovea or the PRL to the fixation target, and the optical axis, which is an imaginary line perpendicular to the frontal surface of the cornea. It intersects the pupil and it passes through the center of all the refractive media of the eyes. So we measure angle kappa using an eye tracker designed by Moshe Eisenman from the University of Toronto, and he calls it an orthomagic eye tracker. The nice thing about this eye tracker is that calibration is automatic. It doesn't require the standard calibration looking at different points. Oh, thank you. Hello? And it has two configurations of infrared emitters. I'm showing you 3, but it has also 5. The bottom infrared emitter is always present. It has 2 cameras. And the display, the visual distance can be modified by using a different display, which shows the target at 40 centimeters, 100 centimeters, and 6 meters by means of a mirror. I don't know if you can see at the very end, there is a fixation target at 6 meters. Now, from the orthomagic eye tracker, we obtained the differences between angles kappa of controls. In this particular study, we didn't go to the literature, we measured our own, and there were 5 controls, that is 10 eyes, and 9 patients with bilateral age-related macular degeneration. We transformed them into world coordinates, and then we used a microperimeter, we used an MP1, to verify the monocular PRLs. Now, the agreement between the orthomagic and the MP1 was quite good, and that gave us the confidence in trusting the binocular measurements made by the orthomagic. Now, the orthomagic system starts with a number of geometrical assumptions about the geometry of the eyeball. The eyeball is initially assumed to be a sphere, and so is the cornea. The algorithm iterates and reduces the error. So here you have the pupillary axis, that is when the optical axis runs through the middle of the pupil, and the visual axis, and of course gaze is directed along the visual axis. This image shows the angle kappa on the retina of a right eye with an intact fovea, and you have the two components of the angle kappa, the fovea. And I just want to point to the fact that we use the optic disc, the middle of the optic disc, as a reference for our distances. And here is how we measured the PRL distance from the middle of the optic disc in the right eye of a person with age-related macular degeneration. Now, there are three basic problems in inferring the location of the PRL with any eye tracker. First of all, there may be more than one PRL, and that is especially true in the early stages of the disease. The second is that the PRL may change when you switch from monocular to binocular vision and back. In this particular table, please note in the pale blue cells, the agreement between the monocular measurements made by the microperimeter and the monocular measurements made by the orthomagic. Now, patient P6, when it came a time to see the target binocularly, the right eye moved, and looking at the coordinates, you can see that the target for the right eye, which is the worst eye, if you look at the acuity on the left side of the display, whatever. If you see the coordinates and compare those with the coordinates that we obtained from the MP1, you can see that this person has been rendered monocular. In other words, the image of the target has landed on the scotoma, viewing binocularly. Patients like P6 have many issues. First of all, the reading is slower. They exhibit binocular inhibition. And as we saw before, they may change the monocular PRL when viewing binocularly, especially making it difficult because this renders them monocular. Now, binocular inhibition is a condition in which any measure you take, acuity or reading, is worse with binocular viewing than with monocular viewing. And this is quite an eloquent description of binocular inhibition made by a patient showing how viewing binocularly is a lot worse than viewing monocularly with a better eye. The third problem is the PRL may or may not change with the task. We have two studies in which we measured the PRL during fixation, either in the light or in absolute darkness, complete darkness. And the PRL doing the vestibular ocular reflex. People had to imagine, for the fixation task, people had to imagine a target straight ahead. And for the vestibular ocular reflex, they had to imagine the target and move the head. However, in another study, we showed that the PRL changes with the task. So in smooth pursuit, we found that for horizontal smooth pursuit, 8 out of 10 patients showed a PRL to the left of the scotoma, whereas for vertical smooth pursuit, the PRL was below the scotoma for 8 out of 10 patients. Now, I have to just warn you that in this particular study, we blocked the trials by direction. If we had combined all the trials, probably the PRL wouldn't have changed. The important thing is that for the same people, the PRL changed depending on the task. It looks like they're simply using whatever is more convenient. So why do we need PRL recordings for patients with central vision loss? Well, if we want to understand their adaptations to natural circumstances, we have to understand, we have to measure their eyes binocularly. We go about the world viewing with two eyes. We move our head, we manipulate objects, we walk, everything with our two eyes open. And this requires that we make measurements not only of point of gaze, that is where people are looking, but also the absolute position of the eyes relative to the head, that is the PRL. Now, before I leave, I want to call your attention to the fact that most of the studies we have done in central vision loss in people with macular degeneration have used adults. You have people with age-related macular degeneration, people with a juvenile form of macular degeneration, Stargardt's disease. But I want to call your attention to a third group of people. These are children, survivors of retinoblastoma, which is a very aggressive cancer of the eye. And for those children who are lucky enough to live in big urban areas with large hospitals and first-rate healthcare, the modern treatments are saving their eyes, which is a very good thing. But in many cases, the treatment has the side effect of producing central vision loss. And we just don't know how such a young brain adapts to low vision. Now, before I finish, I would like to introduce you to what was the Oculomotor lab. I thought about how to do this. I put it in alphabetical order with me at the top, but it's only alphabetical. Lumi is still active. And over the years, we collaborated with many other scientists, clinicians, students, research assistants, et cetera. Our affiliations were with the University of Toronto, York University, and the University Health Network. Actually, one of our best graduate students, Eva Nichvi-Zvedo, will address you very shortly after the break. So keep an eye. Thank you very much.
Questions from the audience? Okay, I can't. Okay, so there is a question here, and I'm going to take it.
Yeah, another source of loss that might be interesting to study are those from trauma. I had the opportunity to study one of the few people in this country, at least, who has their eye damaged by a champagne cork. And the advantage would be that they're younger and don't have comorbidities in the brain or the eye, and are often very motivated to be as resourceful as possible and using, a PRL, their PRLs very dynamically in their eyes to get as much information as possible. I'm wondering if you've had an opportunity to study that a few of those population.
I got your mic. I have another one. I do.
Thank you. No, in the lab, the majority of the patients we studied were people who were enucleated because of retinoblastoma at a very early age, usually between 2 months and 2 years of age. And we did a number of studies on them. These children, they were monocularly enucleated, well, obviously, but they were healthy in other respects, everything. The remaining eye was perfectly healthy. And as far as we know, there are no other comorbidities. So what you're saying is very interesting, but we never had a chance to study them.
We have a question on the Zoom chat, which Deb will read out.
How does measuring PRL help in rehabilitating a person with central vision loss?
Well, I give you a short example, for example, of what it is to not knowing anything about your scotoma or anything about your eye movements. pretty you did work with people like this. They can be helped, but they often come to the clinic saying, you know, things appear and disappear, and I'm completely lost. Training the PRL is useful, and you can train a PRL to be above the scotoma, and that helps with reading enormously. A PRL to the left of the scotoma is quite problematic because it has problems in the programming of forward and return saccades. So where you place the PRL has important consequences, not only for reading, but walking, ambulating.
Can I speak loudly?
Yes, of course.
I give it study patients with AFD, and I find that some of them are very good at imaging systems. I ask the some of them are very good at imaging, some of them are not. And so there's some correspondence between the noise and the PRL that's very curious about this. How it's done.
You can. Well, this question is about training the PRL. And yes, you can train the PRL in several ways. We, in the lab, train the PRL using a microperimeter, using biofeedback. So you ask the patient to look up, but not too far up that the target becomes invisible. And so judging from the size of the scotoma, their acuity measures and so on, you decide on an area of the retina which is suitable for the training. And for example, if you train them to move their eyes up, to use their bottom visual field, it's the very first thing you have to train them is not to overdo it. It's like learning to drive. You tend to overdo it at the beginning, but slowly, little by little. In our case, it took a week. Patients would come every day to have half an hour of training. And in the end, they learned to read rather well. I mean, considering the size of the scotomas and so on. Then we moved to a cheaper version, which was using just a laptop. And it actually worked rather well. It was an easy way of doing it. It's just reminding the patient not to overdo it. And we trained the upper retina. In other words, we trained them to look up all the time because in the previous study, we had found that that was the best PRL for reading.
You have a question on Zoom chat?
So the question is there any correlation between PRL and photoreceptor density?
I believe there's not.
Thank you, Esther.